presentation of the work that I've been doing in the last decade. And second, I would like to talk about some, it's like activities regarding the site,
Yeah,
IEEE site activities. So,
sure.
it
Very
has
much
a
beneficial for the students.
yes, social impact effect, and it might be useful or it might be interesting to the audience here.
Yeah.
Okay.
Dipti, you can start.
Okay, sir. So, good evening and welcome to all to our webinar series. So, today we have a webinar on multifunctional filtering antennas for radiation on demand by Dr. Jawad Siddiqui, who is Associate Professor in Institute of Radio Physics and Electronics, and he is also visiting faculty of Royal Military College of Canada. So now I request to Dr. Samok Bhattacharya to give brief introduction about Dr. Jawad Siddiqui, sir.
Okay, so thank you, Dipti, and good evening to all of you, and good morning to sir. So it's a nice privilege to introduce my own sir in my own institute. And let me tell you, before giving the formal introduction of Professor Siddiqui, that we are the first batch to be taught by Professor Siddiqui in University of Calcutta in Department of Radio Physics and Electronics from our first year to the final year. So let me just formally introduce him. So Jawad Yasin Siddiqui is an associate professor in the Institute of Radio Physics and Electronics, University of Calcutta, India. He received his Doctor of Philosophy degree in Radio Physics and Electronics, University of Calcutta in 2005. He worked as a postdoctoral fellow at the Royal Military College of Canada and visiting researcher at Queen's University, Canada at different periods during 2008 to 2021. He has more than 150 publications in peer-reviewed journals and conferences. His research areas include printed circuits and antennas, radar, and nanophotonics. He is a co-principal investigator on stratospheric tropospheric ST radar project at the University of Calcutta. He is a senior member of IEEE and served as chair for the APS and MTTS joint chapter in IEEE Kolkata section and site chapter IEEE Kolkata section. He is ART10 coordinator of the IEEE Antennas and Propagation Society. He is currently the IEEE APS site chair and the member of IEEE Humanitarian Activities Committee. He is also a member MTTS meetings and symposia committee and corresponding member IEEE Technical Activities Board. So without having any kind of further delay, it's over to you, Jawad sir.
Thank you so much. Thank you so much, Shamak, for this introduction. As I said, that this presentation, what I would like to introduce to you, or maybe some of you might have listened to this talk earlier, given by me or by Chin, my co-workers whom I've worked in the last decade. This technical presentation is entitled Multifunctional Filtering Antennas for Radiation on Demand. So, talking about multifunctional filtering antennas, we also had a book which was published in 2018 on this topic. Multifunctional filtering antennas, basically, why do we need filtering antennas? So, as you know, with the opening of the spectrum usage for the ultra wide band, we designed we were starting to design this ultra wideband antenna covering the whole ultra wideband spectrum. But then, with this increasing interest in this use of UWB systems, they were allocated to UWB system. We had the requirement of filtering out some of the frequencies to avoid interference. That was the basic concept of how would you filter out, weed out some frequencies, undesired frequencies in the whole wideband system. If you design a UWB antenna which covers a ultra or a very wide bandwidth antenna, but you'd like to filter out some of the frequencies, how would you do that? So of course there are techniques, or the existing techniques of having a filtering unit before the antenna and designing it, and provision of band notching filtering at the interfering frequencies. It offered a good potential, and in the same antenna can work as a filter and as an antenna. The whole system or the whole design becomes compact. And we have seen a lot of work in antennas having this defective ground structures, and you can do a a lot of engineering in the physical system itself, in the physical geometries, which will tune the frequency, which will filter some of the frequency, which will read out some of the frequency, as well as increase the bandwidth. We know it's all basically a part of the game of how do you design the geometrical design of the antennas and the excitation of what modes that we want to radiate. And of course, this excitation of this modes will give you different form of radiation patterns. So there are some interesting works which we thought we did, and that's what I'm going to share with you. Like antenna plus a bandpass filter, that is an individual design. Now we are moving to a integrated design where the filtering system is becoming a part of the antenna. So in this integrated design scheme, the filter and the antenna is itself treated as a subsystem. What happens then, you don't need a separate filter or a matching circuit which will integrate to the antenna, because again, matching becomes an issue for any antenna, and there's an overall size reduction because the whole system becomes very compact. So that's the reason we need filtering antennas. So when we were looking through the surveying the literature of this sort of antenna structures, what we found that there were lots of modification, the radiators and the ground planes. These radiators and ground plane modification, what it did, basically it provided a unique design which will be applicable to one of the specifications that we are going to use that antenna for. Say if you want to filter out a frequency at 4 GHz, at 5 GHz, or at 5 GHz in ultraviolet system, then the whole system designed this slots and cuts on the radiator or the ground plane. Basically, you have to determine the dimension of the slot or the stub that you are going to introduce on the geometry or include in the geometry, and that is basically a one-off design. So we wanted a design which will be scalable, which will have a like a generalized like design equation, and which can be tuned to any frequency. And that is what motivated this work of designing a compact split-ring resonator loaded ultraviolet monopole antenna with frequency notch characteristics. That is, you have an ultraviolet system where there's a desired notch that you want to introduce a notch. You want to filter out read out that one of the frequencies in that ultraviolet system. So this work, what it does, our work, as you can see here, this is basically an ultraviolet monopole antenna, very simple coplanar waveguide fed monopole antenna. You have this split-ring resonator, which is basically placed strategically on the other side of the printed monopole antenna. Okay, what it does, it provides these are sub-wavelength resonators, which provides a notch which is frequency scalable. The design of the antenna and the SRR contributing to the notch are independent. Independent in the sense that, irrespective of the geometry of the radiator, we have chosen for the proof to show the proof of concept circular monopole antenna, but this can be this can be done by any geometry of the radiator. You can change the geometry of the radiator. If it radiates, you include a split-ring resonator on the other side, and basically it will start to provide the notch irrespective of the geometry of the radiator. This does not tamper the antenna of the ground plane. You see, it's independent of the ground plane of the antenna, because the antenna and the ground plane is on this side of the substrate, where the sub-wavelength resonators are on the other side of the substrate. And this concept can be extended to any coplanar waveguide fed radiator. I will show you how to introduce the concept and what's the critical part of this design. And can be reconfigured for multiple notches using multiple SRR pairs of varying dimension. So the notch frequency will be aligning to the magnetic resonance of the split-ring resonator, which will be excited by the axially oriented magnetic field, which we'll see in the subsequent slides. So this is a coplanar waveguide fed loaded planar ultraviolet monopole antenna. As you can see, this is a very simple circular monopole antenna. You flip it and you see that two split-ring resonators placed in a way where This is the signal line of the coplanar waveguide. These are the common ground planes of the coplanar waveguide. And you have the magnetic field which will pass through. You have to maximize the, you have to make sure that the alignment of the axis of this SRR basically are excited by the magnetic field which passes through the coplanar waveguide, which basically encircles this signal line between the slots of between the signal line and the ground plane of the coplanar waveguide. So these are the dimensions and the substrate we used of 2.33 epsilon r RT right 5880, and these are the SRR dimensions which we use, and these are closed form expressions that we provided in on most of our papers, with which you can basically calculate, empirically the SRR resonance. So once you calculate, once you know the SRR resonance, you would know that this is the frequency that is going to be weeded out or be filtered out from the antenna. So you can have any antenna which can work for 1 to 20 gigahertz, but if you want to weed out some of the frequencies, you can design your SRR by using this calculation. You design it, you place it strategically on the, strategically on the antenna without affecting the antenna performance, and still can weed out this frequency. So that's why we are calling it a filtering antenna. So this waveguide, to understand where to place, now placement of this splitting resonator becomes very critical, because that is what is going to provide you with the filtering. And to give that an idea, the coplanar waveguide, you have to understand the coplanar waveguide mode. So what are the modes that are excited in the coplanar waveguide? So they are the even modes and the odd modes, and the strategic alignment of the SRR becomes critical, because when you align the SRR in such a way so it maximizes the magnetic field which passes through the axis of the SRR, that is when there will be circulating currents of this conducting like rods of the SRR, which will provide the magnetic resonance, and which will weed out the frequency, filter the frequency. So the magnetic field lines must pass through the axis of the SRR for optimal excitation of the magnetic resonance of SRRs. The SRRs were strategically placed on top of the coplanar waveguide slots between the signal line and the common ground plane of the coplanar waveguide field. And this is how it looks. Okay, this is the magnetic field. It should pass through the SRR. So irregular placement of SRR will not yield the desired effect. You have to understand the physical concept, why it's exciting, and where you have to place the SRR. That's why you have to align the SRR in a very, very strategic way. What it does, it provides there is a constraint, like this alignment of SRR. If you place a pair of the SRR, then the dimension of the SRR are limited by the size of the signal line. Because again, if you want to have for impedance, characteristic impedance, you have to design a signal line at the ground plane of the slot. This will give you for certain dimension, which will provide you with a characteristic impedance of say 50 ohm of the coplanar waveguides of this transmission line. So you have to understand like the dimension of the transmission line, and you have to align the SRR in a particular way to excite. So again, these are the calculations. I'll refer to the paper at the end of my talk, which will give you an idea of how to calculate the SRR resonances with the splitting resonators, where you have to calculate the equivalent capacitance and the inductance, and then you can formulate it to yield the desired frequency. Mathematically, empirically, you can formulate. So there was these equations were taken for FE term, and most of the work has been done by like authors 50 years back, and we are using the same equations and to yield like good results in our work. So if you see the surface current distribution, this is one of the SRR which dealt at which yielded a notch at 6.34 gigahertz. You can see that most of the currents are concentrated in this area in the transmission line, whereas the excitation of the antenna is minimal. Whereas at 4 and 8 gigahertz, on the left-hand side of the notch frequency, the right-hand side of the spectrum of the notch frequency, you can see the antenna is pretty much very excited. As you can see, the current standing waves on the periphery of this circular monopole antenna. So this will give an idea of why the filtering is happening, because the SRR is basically getting excited by the magnetic field of along the transmission line, and basically the field is not able to excite the radiator as such. This is the comparison of the simulated and measured, the reflection coefficient magnitude, the reflection coefficient plots, and you can see the measured and the simulated plot, which shows this this antenna working from almost 2.2 gigahertz to around 10 gigahertz. Whereas when we use the SRR, it yields a notch at 6.34 gigahertz. Okay, the measured notch at 6.34 gigahertz. So that is how you can see that it yields this corresponds to the resonance frequency of the SRR. Okay, so now you design an antenna, you design an ultraviolet antenna, you design an SRR very separately, you place it strategically on the antenna, and depending on the SRR resonance, what is the dimension of your SRR or your subwavelength resonator, this will yield a notch frequency in the whole desired band of the antenna, working antenna. But when we see the radiation pattern, as you can see here, the radiation patterns at 3.1 gigahertz, at 6 gigahertz, just before the notch frequency, and at 10 gigahertz, it is a perfect monopole type radiation pattern, where what you can see here with the E plane and the H plane radiation patterns at different frequencies of the fabricated antenna. And when we measure the gain, as you can see here, you can again see a dip. Obviously, like when it's a filtering antenna, you can see the whole ultraviolet antenna radiated as it's supposed to radiate, whereas you can see a notch at the undesired frequency. So you can introduce a notch at that frequency, and this notch can be scaled, frequency scaled, depending on the SRR resonance, as I said. And this work was published in Transaction in 2014, and it has been cited almost 190 times in the last 7 years. So you can see this is a 3D radiation pattern, different frequencies, as you can see, as it comes to 6 for our desired frequency. It provides a notch at that frequency. Okay, now let me come to for multiple patches. Now, when you want multiple notches, this open up a lot of ideas to work further. When we design multiple notches, what we can do, we can maybe elongate the transmission line a bit further, so that there's space for multiple SRR, placement of multiple SRRs, and have multiple SRRs of varying dimensions. When you put multiple SRRs of varying dimension, we saw that you can yield a dual band, dual filtering, a dual notch, 2 notches or 3 notches, depending on the space that you have to place your pair of SRRs, or if the dimensions are in close proximity, if the resonance can overlap, you can get a wideband filtering of the antenna. And this multiple notches, this can be realized by adding more number of SRR pairs with varying dimension along the coplanar waveguide line. And this method can increase the feed length of the antenna, whereas you can get more notches. And this is how the same geometry, we just elongated the ground section, the transmission line section of the CPW feed, and we placed 2 pairs of SRR on the other side. We printed 2 pairs of SRRs, and as you can see, these are the dual frequency, dual SRR, and wideband notch and dual frequency notches. So you can see 2 distinct notch at different frequencies. And if we can overlap those frequencies, if we can make the geometry, very closely tuned of both the SRRs, you can have a wideband notch. So depending on what range of frequency or how sharp you want the notches, you can literally tune your antennas or design your antennas in that way. But again, you can see that you are not at all affecting the radiator or the ground plane of the antenna. So this is how it looks, and this is the gain, realized gain plot. So you can see again in the gain of this frequency, you can see the notches, which corresponds to the SR resonance. And this is the gain plot, which shows good gain over the whole range of frequency, except at the wideband notch, where the SRs are designed to yield a filtering. Now, the most interesting work are not these works, but this work which came up with a complementary design of a complementary notched ultraviolet antenna and a narrowband antenna. Like now, we have an antenna which will work in a three-way configuration. Like it will give an ultra-wideband response, it can give a frequency notched response, which I showed in my earlier slide, whereas it can also give a narrowband response. Now, what we did in this work is we translated that notch frequency into a radiating frequency. That's why we if you see the title of this work, I say that it's radiation on demand. Now you are having an antenna, one antenna, single antenna, which is working three-way in a multifunctional way. Like it's providing a ultraviolet frequency operation, it's providing a notch frequency operation, it's also providing a narrowband frequency operation, and which can be very much used in the cognitive radio applications where you have a sensing ultraviolet antenna and you know, like a reconfigurable antenna or with narrowband frequency. So how it's done, there are three configurations you can that has been shown here. Like configuration, a normal configuration is without the SRR. Say it's an ultraviolet antenna. The notch frequency will be an SRR with the notch frequency with the SRR, which will give you a notch frequency. Now, if these are the gaps of the SRR G1 and G2. If you close the gaps, this antenna will restore its ultraviolet nature. Okay, so if you close the gaps, instead of the split ring resonators, if they become closed ring resonators, this antenna will basically radiate ultra in the same fashion as it would have radiated without the SRRs. Okay, so this will give an ultraviolet, restore the ultraviolet frequency operation of the antenna. The moment you put the gap, you place these gaps and split the rings, this will yield a frequency notch response. Okay, now again, the third configuration, which I found out very accidentally, is if you short the ground plane and the signal line of the coplanar waveguide, what will happen? You know, nothing should pass through. This is shorted. Of course, depending on the thickness of this line, what it yields is that it yields a narrowband response. That what has been notched, what was working as a notch frequency, is now basically radiating, and the rest of the frequencies, rest of the band, spectrum have been suppressed, which we'll see in this design. Okay, so with one antenna, if you have a shunt wire, which is basically shorting the signal line of the ground plane, and the SRR, you are basically having a narrowband response. With the SRR only, you are having the frequency notch response, and with a closed ring resonator, you are restoring the ultraviolet response. And that's the beauty of this antenna. As you can see, so to show the proof of concept, we just deliberately shorted the signal line and the coplanar waveguide with a shunt post. Now, again, this has to be very strategically placed. Should be exactly on top of the axis of the SRR, which is printed on the other side of the substrate. And now you can see here in this design, we showed the earlier graph, like this is the the S11 plot of the frequency notched operation. Now, the moment you put a shorting post, this transforms into a very sharp narrowband response. Okay, and this is again, when we did the gain configuration, when we tested the gain, this was the SRR loaded gain that we showed earlier. Okay, the moment you place a shunt wire, it suppresses basically all the spectrum, all the spectrum or wideband spectrum that the antenna is radiating, except the one which was yielding a notch. So it's a very complementary response. The complementary response is the response which was yielding a notch is now basically acting as a radiating antenna. And it's very interesting that you are now making an ultraviolet antenna working as a narrowband antenna. Okay, and again, if you change the like tune the SRR dimension, you can basically tune this narrowband frequency, and that is very interesting. Okay, and if you close the gaps of the split ring resonator, transform the SRR into a closed ring resonator, what you yield is a very again restore the ultraviolet response. So that's why we called it this antenna as a multifunctional antenna, because with one very simple single antenna, you can basically work in 3 different modes. Like you can make it work as ultraviolet antenna, make it work as a frequency notch antenna, or make it radiate as a narrowband antenna. So you're basically yielding 3 distinct characteristics from one single simple antenna. And that was the beauty of this work. So this multifunctional antenna, what we did, this is the group delay plots. And this is a plot which shows the magnitude of the pointing vector. What we saw that in the frequency notch case, this red part is the energy that's going into the antenna radiating. And what happens when we take the antenna dimension, and we can see that this green line, basically this the pointing vector tells you that no power is going in this direction for this frequency. This is the frequency axis, okay, for this frequency. Whereas when you use a shorting post, you can say only this is the red part, that's most of the power is going basically for that frequency, which was basically yielding a notch, and whereas it's suppressing the rest of the frequency. And when we saw the radiation pattern for the frequency that's working as a narrowband frequency, we can see that this again is a very beautiful, monopole type response, which we expect from that antenna. What we did now for the next part, instead of using a shorting post, we tried to place some pin diode so that we can reconfigure it in real time. So we loaded a pin diode, used a bias state to excite this antenna. And we did this in the Royal Military College in Canada. And what we did, we did an experimental setup to see a real-time performance of this antenna. And you can see this is the real-time antenna when the diode is on and off condition, where the antenna basically toggles between a frequency notch antenna and a narrowband antenna. And I have a small video you can see here. You can see the response. So this is a frequency notch response, the S21 response of the antenna. And so you can see the gain is basically, there's a dip in the gain at that frequency, and when the diode is in off condition, when the diode is in on condition, you get a basically up. When this current passing through the instead of shorting post, now when you have the spin diode in 6 when it's active, basically it's radiating as a narrowband antenna. So that is the most interesting work, and it was published lastly in AW in Access in the title it as Active Trigger for Ultraviolet Antenna, Complementary Frequency Notch and Narrowband Responses. So this frequency notch and narrowband responses basically switches on and off, like this configuration, which translates between a narrowband antenna and a frequency notch antenna, which was shown as a single strip. Now we used it as an active antenna using pin diode. And as I said, you can do multiple configuration. Now you can use multiple SRRs, where we use 2 different SRRs on a separate super straight with some SRRs, and yielded different kinds of frequency notches. As you can see, we used a separate SRR, one a superstrate of different dimension and getting two different distinct notches, which we showed earlier with the linear placement of geometrical SRRs. Okay. Then you can also get triple notch SRR. Again, this design was done using by changing the orientation of the gaps of the SRR. So these are circular SRR with rotated inner ring. When we rotate the inner ring, again, it's all basically engineering of the phase and the amplitude. And with which we can do is you can get the same kind of responses which we did in other designs. So we have a paper in IET, I think, where we give this expression and we derive this expression to yield to calculate the notch frequency of the SRR. As you can see, like 3 distinct SRRs with rotated inner ring will give you 3, different types of rotation of the inner ring with respect to the outer gap, and with the 60, 90, and 0-degree rotation, we can yield 3 distinct notches in the frequency. So like if you have a constraint in redesigning the dimension of the SRR, what you can do is we will try to show that you can basically play with the rings, the orientation of the inner gaps, in the gap with respect to the outer gap. If you rotate the ring, that will also give you a tuning effect and will tune the notch frequency. Now, multi-frequency notch. Now I'm going to show another design, which is a multi-frequency notch ultraviolet tapered slot antenna on a very different kind of antenna. We used a resonating, like a monopole type antenna, a printed monopole type antenna. Now I'm going to use a traveling wave antenna. Basically, it's a tapered slot antenna. And this was the tapered slot antenna which I designed almost 12 years, 11 years back or 10 years back. And this has a very, very wide band response. The operating bandwidth was from 400 megahertz to 10 gigahertz. Okay, it was termed as the antipodal tapered slot antenna. This antipodal tapered slot antenna has 2 very simple elliptical strip conductors on 2 sides of the substrate, and it's supported by a Bayesian transition using a microstrip line to a parallel strip line, and it basically excites these 2 sides of the elliptical conductors, which gives a very wide bandwidth of 400 megahertz to 10 gigahertz. And these are the design equations for this antenna. Now, what we did is we used the antipodal tapered slot configuration. There are 2 ways to feed this antenna. You can use a coplanar waveguide or an antipodal configuration. This antipodal configuration is nothing but a Bayesian order from a microstrip transition to a parallel transition, which is microstrip, is an unbalanced line, and the parallel configuration is a balanced configuration. So this is the part of the Bayesian which consists of the microstrip line and rapidly tapering ground plane, forming a parallel line, which will excite the antenna. What it does is that the feed structure becomes very simple to design, and the bandwidth is pretty enlarged than the normal coplanar configuration that you have of a coaxial line to a slot line transition. So this is the Bayesian part, and this is the E plane and the H plane. So the E plane is the plane consisting the direction of maximum radiation and the orientation of the electric field vector. So we know the electric field vector couples from this conductor to this conductor. So this will be the orientation of the electric field vector, and this is the direction of the maximum radiation in Y direction, and the electric field are in X direction. Okay, when we have the electric field in the X direction, then the direction of maximum radiation in the Y direction, which that will form the XY plane will form the E plane, or the azimuthal plane will form the E plane, because by definition we know that the E plane is the plane which consists of the direction of maximum radiation and the electric field vector. And if you take the orthogonal plane, this will form the H plane, because this is how the magnetic field will encircle, because this is the electric field. This will be the magnetic field in Y direction, sorry, in Z direction, and then the YZ plane will form the H plane. I'm saying this because now what we did is we used the splitting resonator to place, strategically on this radiating on this radiating line, in this direction, on this space of this antenna, to weed out or to filter the antenna of the, for the filtering purposes, to weed out the undesired frequency. So first we have to understand how this antenna works. So the electric field transformation from the balun to the radiator, as you can see, this antenna, see, this is where the electric field gets skewed. It starts as a microstrip line and goes to a parallel line, and then it gets skewed, and this is how the electric field excites this antenna, and this antenna radiates. These are the standing waves at 1 GHz and this should be 8 GHz, not 3 GHz. Surface current distribution of the radiators. And you can see these are the S11 plot of the antenna, which works from 400 megahertz to almost 10 gigahertz. And this is the peak gain, average peak gain of the antenna, which we again did a measurement. And these are the radiation pattern of the antenna, E plane, copolar and cross-polar radiation pattern of the antenna, which shows a directive type radiation. So now what we did, we used the splitting resonator to place it at a location where we know there will be the maximum of the magnetic field, because this is the H plane, okay? And this is the H plane, that means the magnetic field will be oriented in this direction. Now, when we place the splitting resonator of the radiating aperture, we found that this SRRs can still yield a notch from the frequencies, from the ultraviolet frequency that this antenna is radiating. And we also found that if you place the splitting resonator strategically very close to the microstrip line, you can also use you don't have to use only the coplanar waveguide. Even if you know how the magnetic field is oriented, the fringing magnetic field, electric field, if you have the fringing electric field, you will also have the fringing magnetic field. And if you can place the SRF in a very close proximity to the microstrip line, you can also yield a notch in the frequency, which I've shown in my subsequent slides. Again, this was the calculation of the SRR resonance. Again, is very clearly defined in this paper, in transaction, which was published in 2018. And as you can see, these are the SRR. Just place it. It's a separately designed SRR, fabricated SRR, which was very, very strategically placed on the radiator, and a very, very well located in a well-planned design, where we just separately designed the SRR splitting resonators and just placed it on the radiator. You can see that, we'll show you in the next slide, that this will really yield a stop band response. Here you can see SRR on the TS aperture. You can see three distinct, depending on different types of SRR, the dimension of the SRR, you can see there are 4 different types of SRR, 4 distinct notches over the ultraviolet band response. Okay, so when you have that SRR yielding to different different dimension, different geometry, and if you can compute those frequencies of what is the undesired frequency in that response, which is the frequency you want to weed out or filter, you can design your SRR in those frequencies and just place it on top of this on top of the ultraviolet band antenna on the radiating part. But again, what I said, that you have to understand that what is the orientation of the magnetic field, because if you want to optimize the SRR resonance, you have to make sure that the magnetic field maximum is optimally exciting the SRR if it passes through the axis of the SRR. Okay, and again, this is the gain plot, realized gain plot, and with frequencies, you can see with SRR 1 and 2, you can see these are the notches that is yielded by the SRR. So again, if I go back, this is how you place the SRR. And again, if you place the SRR on top of the microstrip line, you can also yield the notch which is again, it's another study. So you can calculate the SRR resonant frequency. Of course, these are for square shape SRR, and you can see the equations in this paper. Okay. Now, like I said, now these are placed on the radiator because we know that the magnetic field is oriented in this direction. This is the H plane, so we know that this is where we'll get the maximum magnetic field. And if you place the SRR basically yields a notch. Since these SRRs are subwavelength resonators, that's why it does not basically affect the radiation. So we have seen the radiation, check the radiation also. It does not tamper with the radiation. It just stops radiating at that frequency. Otherwise, the taper slot antenna radiates as it was radiating without the SRR. And then if you place two different SRRs on the microstrip line also, which is on the baleen of the antenna, you can also get very distinct notches. Because if you know the fringing of the electric field, the fringing of the electric field along a microstrip line, there's a very small fringing. And if you know the orientation of the magnetic field, and if you can make this magnetic field pass through the axis of the SRR, this will stop this, stop the frequency. The SRR will start to resonate, and it will stop the transmission of the, frequency corresponding to its resonance, and that will yield a notch in the desired spectrum. And as you can see here with SRR loaded, like taper slot antenna, you can see that the antenna is basically, it shows the taper slot type of radiation with a directive radiation in the E plane and the H plane. And the SRR basically, since they are subwave resonator, they do not have much impact on the radiation pattern. So, a lot of other groups, there's a group in Italy, Bilotti and group, and their group, they also did this work. They used the SRR on a dual ridge horn antenna. And incidentally, that was the work which even we did, but we didn't publish at that time. We placed the SRR on top of the dual ridged horn, placed in such a way that is this frequency notch at that corresponding to the SRR geometry. So these are the references of my work that was published in in different journals. So these were published in AWPL letters, and this was in Transaction, and this was in AWPL letter, and this was in Axis. And then we had a couple of publications in IEEE magazine. So that's my work. So we designed some proposed design in designing filtering antennas and multifunctional antennas. But my most interesting design is the multifunctional antenna, in which an antenna can work with three functionalities of a narrowband response, an ultraviolet response, as well as a frequency loss response. And these are all done with strategic placement and alignment of split ring resonators. We do not claim these as metametrial antennas. That was the objective when we started to do this work, that we do not claim this as, a lot of metametrial work was going on, and metametrial term was used or misused. So we just simply showed that these are nothing but subwavelength resonators, with which you can design, which can give you some, very understandable characteristic of the antenna, and which can design these notches. And by the way, in this context, I must tell you that split ring resonators, regarding split ring resonators, you can get a lot of information about split ring resonator, the design equations, from the 1956 book of Shelkunov. He was, if you go through his book, Shelkunov's book, I had that book, I can share I'm not sharing with you now, but I should have shared with you. But in which he has explained how to use a split ring resonator and how you can design a split ring resonator and what will be the resonant frequency of the split ring resonator. Okay, with that, I acknowledge my collaborators, Dr. Shah, Chinmoy Shah from IST Trivandrum, Dr. Antar, whose lab I've extensively used for this measurement, my another worker, Chitrajit Sarkar, who is in Kolkata, and Latif Sheikh, who is again a co-worker who is right now at ISRO. And this is the book I was talking about. And you can have a look at this book for multifunctional ultra-wideband antenna. And that's it. Thank you.
Okay, so sir, thank you very much for the wonderful talk. So sir, so we have received a few questions. So if you kindly permit me, can I just
share? Sure, please.
Yes, please. The first question was there from Dr. Pranjal Boda. Instead of reading the question, let me first see that whether the person is there or not. Dr. Boda, are you here? Dr. Pranjal? Hello?
Yes, I am here. I am there.
Yeah. Please go ahead. Please go ahead.
Yeah, so actually it's a very nice talk. And I want to know that because the use of SSR has been shown, so is there any kind of formulation?
Yeah, we have a formulation. We have formulation as I showed in my. Can you see the presentation? If you see the.
No. Okay. Can you please share one second, sir?
Yeah, I'm just sharing. Can you see?
Yes, we can see. We can see. Yes.
Yeah, this is the last. This is the complete form which we used when we presented in this transaction in March 2018. It was published. You can, in the appendix, you can see the whole calculation of the SRR of a square split ring SRR. Square shape SRR, and you can find the calculation in this paper. And this has very accurate that what we found out in the measurement and corresponding to the measured values. So maybe this is the paper that he can refer to. We have lots of other calculations too, but I would ask you to refer to this calculation because this has been trimmed and more accurate.
Okay, just a placing of the SRR over the strip line that you have shown, beneath the strip line actually, first of the two or that slides. So there itself, where to place exactly the SRR?
Again, the placement of the SRR becomes critical because that is the that is the most critical and part. You have to place the SRR. Again, go back to my slides. You can see, this is how a coplanar waveguide works. That if you consider two modes, the even mode and the odd mode, this is you have to that the magnetic field will pass the slots, right?
Okay.
So you have to place the SRR whose axis of the SRR, this axis of the SRR should be aligned in alignment with the magnetic field of the coplanar waveguide. So this axis of the SRR should be just at the bottom of this slot. So you have the coplanar waveguide, you have the slot, you have the slot lines, right? You have the signal line, ground plane, or the slot line. The SRR axis, the center of this SRR should be aligned to the slots.
Okay. Yeah. Thank you.
Okay.
Yeah. Sure.
Sir, also I got some questions from Dr. Jeet Banerjee. Are you here, Dr. Banerjee?
Yes, sir, I am here.
Yeah. Please go ahead. Instead of reading your question, please.
Okay. Good evening, Jawad sir. It was an amazing presentation, and I have gone through your book on multifunctional antennas. It is amazing, actually. My question to you is, we have seen in the present literature that we can explore connected split ring resonators across the feed line of CPW feeds, utilizing their contradirectional magnetic fields, and we can cause band notch. So my question was, have you explored this contradirectional magnetic fields of CPW gaps in your any works of yours?
No, we haven't. We are more concentrating on the fact that we are trying to design a multifunctional antenna. We showed it with RF with diode with pindouts, right? We are trying to do it with MEMS.
Okay. Okay, sir, I have two more questions. First question is, where do we, in real life, we apply this ultra-wideband MIMO antennas? Where do we apply these UWE MIMO antennas? And the last one is, suppose if, when can I claim that an antenna is multifunctional antenna? If it is, if my antenna is possessing an ultra-wideband response, along with that, it is covering some multiple bands, say lower bands at 2.4 gigahertz or say other bands. So can we claim that it is a multifunctional band antenna?
The reason I said that, if you see, the reason I said that if you see the title of my talk, it's multifunctional filtering antennas for radiation on demand, right? The radiation on demand, the reason I'm saying that is because of this. Now you have a radiation on demand, like you can switch off the radiation, you can switch on the radiation, like as you demand it, okay? In the video that I showed, that we have used printouts, like if you can literally switch on and switch off the radiation, and you can toggle the radiation between a narrowband radiation and ultraviolet radiation, okay? And these are not MIMO antennas. The application will be cognitive radio application, where, you know, cognitive radio, when you require multiple antennas, okay, when you require multiple antennas, and you have placement of these antennas, multiple antenna in one location will give rise to port coupling, and the proximity for the port isolation becomes an issue. You have multiple ports, the matching becomes an issue. What we have shown is that we have one antenna which can work in three distinct functionality. One functionality will be as an ultraviolet response, one functionality will be as a narrowband response, and another functionality will be as a frequency notch response. And this frequency notch response and the narrowband response are tunable. What we haven't showed here is that I have only theoretically showed that if you close the gap of the closed ring resonator, CRR, it yields an ultraviolet response. So now, if you plan to have some kind of pinned out shorting post or pinned outs, which can activate or actuate this closing of the gap of the split ring resonator, you can restore the ultraviolet response of the antenna. So that is why when you have one single antenna with single port, but just by toggling of active devices, you can make the antenna work with different functionality. That's why we termed this as a multifunctional antenna. Okay.
Thank you very much, sir. It was an amazing presentation, and your book is also very motivating, and it gives a depth of multifunctional antennas. Thank you very much.
Thank you so much.
Sir, I have got another couple of questions from Miss Madhavi Chandra. Madhavi, are you here?
Good evening, sir. Yes, sir.
Yeah, please go ahead.
Sir, actually, I wanted to know this SSR concept, sir. If we are making some micro strip fed or strip line fed patch antenna, or like you have shown in your slide, another way of having Vivaldi antenna is like strip line fed other configurations. So where we can keep this SSR, sir?
Yes, again, let me come back to the slide. Can you see this strip line configuration here?
Yes, sir.
Now, you know, like this is how a micro strip line works, right? These are the electric field lines. Like there will be some fringing electric fields on the two sides, right?
Yes.
Now, when you have a fringing electric field on two sides, if you can decompose it, what will be shown vectorially? Then you have a component of the electric field in this direction and in this direction, right? Because these are skewed electric fields.
Yes, yes, yes.
Okay. Now, when you have a skewed electric field, then you will have a skewed magnetic field too. Okay. When you have a skewed magnetic field, you know that the magnetic field will be in this direction, in the very, very close, in the very small and close region of the microstrip line. If you align the SRR, like if you can see here, if you can align the SRR in very close proximity to this line, the magnetic field, magnetic field which is arising due to the fringing of the fields can excite the SRRs, and that is what we have shown exactly here when we place it very close, in very close proximity. That's why we separately design the SRR, so there's a substrate layer. There's a substrate layer so that it doesn't, like the SRR conductor doesn't touch the microstrip line conductor. And we brought it very close proximity, and the closer we brought, the more closer we brought, the more sharper we got the notch. Okay. Wait, here you can see. So you have to understand the underlying physics of how you have to place the SRR, because the SRR again will be excited by the magnetic field. If you have if you know how the magnetic field lines are encircling your antenna, or where they're located, where it's being excited, you can place your SRR in that location to get it, or get the optimally excite the SRR.
Okay. Sir,
yeah.
Yes, go ahead.
Sir, I have another question also, sir. Like if I have one antenna which is dual linearly polarized, suppose a horn antenna which is having 2 feet, sir, and square waveguide kind of a structure. So in that case, if I want to filter out some frequency for both the polarization, then how to place this SSR, sir?
Doesn't matter, just place it on the aperture.
Okay.
Okay. Place it on the aperture, because you know how the magnetic field are lying on the aperture, right? So you have to just place it. You have to make sure that plane of the SRR corresponds in such a way that the axis, basically the magnetic field cuts or passes through the axis of the SRR.
Thank you very much, sir. Thank you very much, sir.
You can try it in the lab, because that's how I found this all accidentally. I just tried out with different shapes and dimension and trying to figure out how this worked, and I got it, and then I did some extensive research and found this thing. So if you play with your instrument, if you know the underlying physics, it's very it'll be very interesting and useful to design new configurations.
Thank you very much, sir, for this informative talk, sir.
Thank you. My pleasure.
Yeah, so thank you very much, sir. So any further question, we can take another few, 1 or 2 quick questions before sir will move to the next presentation. Maybe another 1 or 2 quick questions. Deepti, you are having any question? Hello, Deepti Ranjan. Maybe he's having some problem. Yeah.
Okay.
Mr. Shogata, you are having any question?
No, sir.
Okay. If you want to ask, so you may ask. So
yeah, you can.
Yeah, please.
Hello.
Please.
So thank you for this wonderful presentation, sir. So I have one asking, sir. So in this slide, it is CPW fit or the partial ground fit. It is partial ground fit antenna, sir, in this slide?
I think I showed a CPW fit antenna.
CPW fit, okay. So the split ring slots have been used here, sir?
Sorry?
In this diagram, in the partial ground plane, split ring slots or split ring configuration, metallic configuration have been used, sir?
No, split ring, these are not complementary SRR, these are SRR. I think the split ring slots is complementary SRR. These are SRR, conducting metallic SRRs.
So they are etched out from the
no, it's not etched out. It has been separate. Yeah, if you can. Okay.
They are etched out from the CPW plane, or sir, they are plane?
No, it's not on the same plane. It's on the other plane.
Okay, sir. I have that confusion. Okay, sir.
Okay. You flip it and it's printed on the other side.
Okay, sir. I had confusion. Okay, sir.
Okay.
Thank you, sir. Okay, sir.
Sir, I have one thing that in my mind. If you suppose use instead of SRR, if you go with complementary SRR, what will happen?
Yeah, complementary SRR, it can yield, but how will you place it?
Now, suppose in the back plane, if you just etch it out and make a slot by using CSRR, so what will happen?
Yeah, that'd be interesting, because what you can do, you can keep a ground plane here, right? But then it will be a ground plane, grounded CPW. It would not be a grounded CPW. If you have, you can have a grounded CPW with SR, with complementary SRR. Yes, that can also be done.
Yeah.
Okay.
Yeah. Yes, that's what I was just wondering, that whether it is feasible or not.
Yes, you have a grounded CPW. So again, for grounded CPW, all the dimensions will change. But then it will be interesting. It will be interesting to see. Yeah.
So I have another question, sir. Can I be allowed, sir?
Yes, please. Go ahead.
So if we place the CPW, on the CPW plane, if we make some slots like split ring slots, they are feasible for any band notch characteristic?
Yeah, obviously that was what has been done before, right? They have been placing slots and cuts on the radiator and the ground plane, because if you put it on the radiator, there'll be image which will form with the ground plane, right? For this monopole antennas, you have a ground plane, so you will get some form of distortion. Because we are including some kind of perturbation or distortion in the design, just to get them, because we want to filter on that frequency.
So sir, they are related to DGS. We can say it's the DGS also.
If you have a coupler, yes. If you put some kind of perturbation on the ground, it can be called a DGS, or defective ground structure.
Okay. Thank you, sir. Thank you.
Welcome.
Hello, Professor Siddiqui.
Yes, sir. Yes, sir. Please.
Yeah, you have a very nice presentation. Was part of it I heard from Dr. Chinmay earlier, the initial. You said you are not using the term metamaterial.
Right.
You just elaborate on that, because when we say SRR and metamaterial, we use it in both ways. So why you avoided that term metamaterial?
Because metamaterial, again, we should use it in form of a medium, right? When you have like a medium with the SRR and showing a double negative characteristic, or negative mu characteristic, a negative permeability characteristic, that's when probably I would choose to use the term metamaterial. One, and secondly, the split ring resonator, I found about split ring resonator in Shelkunov's book, which was published in 1956. Long before like Penry shows his work for use of split ring resonator as metamaterial. So it's just I would call it sub-wavelength resonators, and using sub-wavelength resonator as a single unit of SRR or a pair of unit of SRR, I used that SRR and designed this antenna. So that's why I refrain from calling it a metamaterial antenna. But again, what is there in a name? Like, we can name it anything, right?
Yeah, that's sure. But in many papers we see now metamaterial antennas. But I don't know whether
that's what I think.
Right.
I think things are changing, because right now they are not directly saying metamaterial antennas, but the terminology is changing. The phrase is changing to metamaterial inspired antennas.
Yeah, yes.
So when you call it inspired antenna, that makes sense. Because the moment I believe if we use the term metamaterial, then we should, we should respect the term and have a medium which will provide, like a backward wave or negative permittivity and permeability.
Yeah, sure. Because in many publications we see that it's not correctly used sometimes.
Right, exactly.
Okay. Thank you very much.
Thank you so much, sir. Thank you so much.
Sir, I want to another question. I don't know that whenever you are having the band stop characteristics, what's about the phase response? Do we have to concentrate on that one also?
Yes, lots of it can be done, because if you want to study why is the band stop and band pass characteristic, we are having both band stop and band pass characteristic, right? And that if you study the phase response, you get a lot of like interesting an idea. Like you can really pinpoint the reason why it's happening, right?
Yeah. Okay, maybe another one quick questions from anyone. Professor Raghavan, if you want to ask, please.
Nothing except my observation of a great person.
Oh, no, sir. Please. Thank you so much, sir. Thank you so much for your kind words. Thank you for being present here, sir. It's my pleasure and privilege to see, stalwarts like Professor Anand and Professor Raghavan here in our talk. Thank you so much.
Yeah. May I also request Dr. DC Bande sir, if you want to say anything? Hello, Bande sir, can you listen to me?
Yeah.
Yes, sir.
I can only compliment Dr. Jawad for his excellent presentation. I was knowing about his work because that I must papers and other things and the way they were working on this particular field from a long time, maybe from the time that Chinmay was doing the work with him. And it was very excellent work. They are working in the very good field, and I have seen their book. I have gone through their book also. And the paper, I keep on going through their paper.
Sir, if you remember,
I check for their papers.
in 2012, we facilitated visiting a laboratory for some for the fabrication of the antennas or some of the splitting resonators for Chinmay's work. Thank you so much. We have long association with Dr. Pandey, and he facilitated the fabrication, the characterization in the slab in LRDE when we visited Bangalore in 2012. Thank you so much.
Yeah, I did.
Yeah.
Wish you all the best. Wish you all the best, and that you are doing an excellent job. He's
Thank
doing
you,
an excellent job.
Thank you, sir. Thank you, sir.
Professor Shomak Bhattacharya.
Yes, sir. Yes, sir.
Just 2 minutes. I just want to tell. Can I tell my opinion?
Yeah, please go ahead.
Actually, we have very valuable participants across the country. Almost every state has been represented. I went through the participants. We have got EMC Man of the World, Dr. DC Pandey, and the first FSS stalwart. Many may not know that he is the first person of India who is in FSS, Dr. C.K. Anandan. The way in which the wonderful question he asked, metametal X-pad and metametal antenna. Then youngest popular FDP organizer, Dr. Shomuk. It is not because he permitted me to talk, but very promptly he sends the material to the research scholars. That shows his service to the antenna community. Only one thing I want to say, Professor Jeet Banerjee asked, what is multifunctionality? I can very well say the speaker himself is an example. Multifunctionality, you tell a topic, he will tell. There is hardly anything which he cannot know. More than that, the speciality is his way of answering the questions. Wonderfully, he has answered. There is no FDP or international conference without Dr. Siddiqui, and I really feel fortunate that both Dr. Siddiqui and Dr. Shomuk, they were together, of course, along with Dr. DC Pandey also. They were there and making NIT Trichy proud 2 years before. So let me once again thank the organizer for organizing wonderful, different kind of lectures. Thanks you all.
Thank you so much. I would have loved to be present there physically. I have the desire to visit BHU definitely in my lifetime.
Yes, obviously.
So
when things feel better, we'll be very happy to host you.
When things are more congenial and suitable.
Sir, you can start you can tell about the site activities. I think that will be very much interesting to the students, especially.
Yes,
they will be very happy. So thank you very much once again for your kind acceptance of our invitation and delivering this beautiful talk.
No, Shoma, thank you. I want to thank you all for being inviting me, and to the stalwarts who are present, sparing their time.
It is basically in fact, always I believe it is basically the work for the students. In fact, they only have suggested your name. I have only done the rest of the thing.
Yes. So I'm also, I also look to do some humanitarian activities, because I'm also associated with SITE. SITE stands for Special Interest Group on Humanitarian Technology. Now, as engineers or technologists, I think we have a responsibility to give back to the society. And as technologists, how do we use technology to serve the underserved population of a community, and what can we do regarding that? So one of the projects that I was executing was to find solution to humanitarian needs using technology. So I would briefly talk about IEEE site, because IEEE site has presence in most of the IEEE societies, and right now I'm the chair of the Antennas Community Society site chapter, site committee. So this site it's special interest group on human use of technology, and what it does, it basically we want members to devote time and talent to humanitarian work, which is consistent with IEEE's constitution, to bring the benefits of technology to the entire world. And some of the major projects which site does is, their aim is to support sustainable technology business initiatives seeking to have measurable impact in alleviating global poverty of energy, healthcare, sanitation, interconnectivity, and such things and so on. So the prerequisite to form a site chapter, I would request students to go through it and see if they can form site chapters, because you need 6 or more IEEE members in good standing. Good standing means they have to be member for that year, active members for that year, and they have to be passionate about humanitarian technology activities. And 3 or more of the signatories must be members from 2 different chapters or 2 different societies. Okay, so it has to be interdisciplinary. If you have 6 members, you can form a site chapter. The cooperative site chapter will need an affiliation with IEEE section or student branch, as you know, because you have an hierarchy and organization unit of IEEE, which has a hierarchy, like you have the section, and then you have the chapter, the student branch chapter, and so on and so forth. So students are encouraged to form sites, and the chair must be a professional member. So the members could be student members, but the chair of the site chapter must be a professional member. And ideally, the student branch counselor or a faculty advisor is basically encouraged to become the chair. And the prospective site chapter will need to submit an application or a petition requesting for the formation of the site. So some of the long-range goals of this site chapter is to incubate, like in this phase, like this is the phase where initial ideas for both technical project and companion business development model is basically thought about and incubated. It's just like a startup, how we do a startup, and it's relatively simple to develop a technical prototype on this time scale. Then you demonstrate. The next phase is to demonstrate. For this phase, IEEE provides extensive funding for development and deployment of prototypes in sufficient quantities to test a business model and to educate. Like the goal of site, like if you want to do something in a remote region, we incubate an idea, we demonstrate an idea, and we have to educate the local people, because it's not possible for IEEE members to stay in that in a remote location for a long period of time. So what you need to do is to transfer the knowledge to ground zero, to local people out there in the region, so that in spite of your absence, when you return back, they can use that technology for development. So one of the idea that I did was to integrate wireless technology with the existing medical application for betterment of humanity. So it's a remote diagnosis and monitoring of patients in rural India related to cardiovascular diseases, because I come from a family of cardiologists. So like that was the very first thing that came to my mind. Why can't I use existing technology and use a wireless technology, we call it the Internet of Things, to do some like fix some problems. So it's a conceptual method to remotely monitor, diagnose vital cardiac signs in patients in underprivileged rural areas. The methodology utilizes technology and digital probing diagnostic tools, a current wireless system to monitor health conditions in patients without direct physical intervention of physicians. And this one I did long time back, almost 2015, before the pandemic. And the idea was set, came to my mind in 2012. So again, why cardiovascular diseases? We all know the global patterns of cardiovascular disease with coronary mortality and the event rates among higher income groups. And CVD is a very, it's a disease, a global disease. And if you see by 2030, the difference between high income countries and low income countries, the deaths due to CVD is going to be in millions, and that's really, really alarming. This was a very old journal from Journal of American Cardiology in 2008. So if you see the Indian scenario, what we found out that the number of heart patients is on the rise worldwide, and the situation in India is even more alarming. And like diabetic patients with high blood pressure, cholesterol have greater risk of heart diseases, and cardiac illness is one of the major reasons for high number of deaths in India. The number of cardiac patients in Kerala is 3 times higher than most of the national average. And that's a cause. And of course, there's a shortage of healthcare providers. If you see the shortage of healthcare providers is mapped in this world map, you can see, if you take the ratio of the population and number of doctors, the ratio is very skewed, and that's alarming. Because you forget healthcare providers, you don't, how could you get specialists, especially like cardiac specialists. So what we did is I went to my village, after I went back from Canada in 2011, and this idea came to my mind was when I visited my village, and there's no railway station, no municipality, and no proper drinking water. But what they had is, and there's no healthcare system, right? We know some of the villages didn't have healthcare system 10 years back, and low employment. But surprisingly, the villages had internet. How did I find out? I had to cancel a railway ticket, so I had to book a railway ticket. For that, I had to go to another village. I come from Murshidabad in West Bengal, so I had to go to another village, and it was a tiring journey. So what I thought I will use the internet, and I could find the internet there, and I could book my railway ticket using my laptop. So the proposed methodology is used to use digital stethoscope and I use connectivity using GSM mobile phone. What I will show is connecting for the physician, which will be in the city, to a diagnostic tool, probing tool in the village, and using that connectivity to detect a problem. So, some of the diagnostic tools that were used was an electronic stethoscope and digital sphygmomanometer, and you can use ECG machines or defibrillators for emergency use. And this is the pilot project which I demonstrated in 2 different villages. One was in Bardhaman and one was in Murshidabad. And if you see this video, you will understand. That's an electronic stethoscope. Which are you? So that's a demonstration what I did in the village. I used a diagnostic tool and the existing internet system to connect to a doctor in the city. That was a doctor cardiologist in the city, who's my brother, and like that's how coordinated. And then what we planned is to generate the skilled manpower, educate paramedics and nurses, and have this kind of system in the village, which could really. The problem is in the village, what happens if a villager goes to the city to see a specialist, the journey itself is huge. Now, lots of people with cardiac ailments it's impossible for them to be mobile, because any kind of stress or journey can, give rise to cardiac arrests. So these are the things that has to be taken into mind, that if we can have a system, we can use technology where we can, stethoscope, I found about the stethoscope, the electronic stethoscope, because the very first thing you think about a doctor is with a stethoscope. That's the very first heart and lung sound that he basically hears to. So if you can send that data, like the data of the acoustic sounds of the lung and the heart to the city doctor, then you can have a system where the doctor can from remotely diagnose. The first basis of diagnosis can be done, with which you can say whether the problem is ill or the patient is ill or the patient is okay. Okay, so that's a very simple thing and a very simple idea which was used. Okay, so the future direction in this respect was to have a wearable sensor-based health monitoring system, which may comprise different flexible sensors that may integrated into fibers, closed elastic bands, and attached directly to the human body. The sensor could measure electrocardiogram, electromyogram, heart rate, body temperature, and arterial oxygen saturation, blood pressure, and respiration rate, and which can be monitored continuously from any part of the world. And there were also, I was thinking of using MEMS-based systems-based miniature motion sensors and accelerated gyroscope magnetic sensors for measuring activity related to signals. So again, this is a very old presentation. It's almost 6 years old. And then only, we thought of having mobile apps, which will be technology-driven healthcare management system, and solar-driven vans with VSAT connectivity. Even if a person, if we know he's having a heart attack, even the availability of basic medicine like sorbitol and those kind of medicines in the village can save a lot of life. Okay, and then we're planning to design locally designed apps like in rural Bengali language, because you cannot expect a doctor to be sitting in a place with like a call center, because they'll be mobile. So when the doctor is mobile, if you have a mobile app with a unique ID of a patient, then that data can be transferred to the doctor, and the doctor on the go and on the run can do the diagnosis. So again, we thought of implementing this in Northeast India and different tribal belts of India, and we tried to name it as Connecting Rural India, CRI, and which we thought could fit into the scheme of digital India and have IoT in remote areas. Right now, the things have evolved in a much better way. There's more better connectivity, and of course, this COVID has showed us that this could have, had it been implemented, like when I thought it would, things would have been really, useful. So like I said, like remote sensing for, like this can fit into smart villages and smart city scheme of things. So we had a poster presentation in World Heart Federation in Mexico, and we partnered with, this is an organization which I'm also a part with, it's Heart Friends Around the World. And, so that is what we did. And what we will do is that most of the medical diagnosis, because my father was a cardiologist who passed away a month back, and like he did a lot of work in rehabilitation cardiology around the world. So he formed this Indian chapter of heart fairs around the world, and where you can provide medical expertise and interact with public healthcare system. What I found out that most of the medical-based risk algorithm are using urban population. There's a huge lack of rural population or rural data. If you use the rural data with the rural demographic data in this risk algorithm, the algorithm will be more robust. Okay, so that is the comment, and that's why I would request students to get involved in site, because site can provide you an opportunity to give something back to the society, and it's very fulfilling and very rewarding. If you see that your help with the use of technology can help the poor people who are underprivileged and deprived, that will give you a lot of satisfaction. And that was the my objective to give this presentation. Thank you.
Okay, sir. So thank you very much for this wonderful presentation. So if any one of you have any kind of questions or suggestion or comments, please go ahead. Any one of you, please. Jawad sir, I don't know. I am asking that whether is it feasible for the students from from a particular branch, if they can't collaborate with other branches, so is it possible to get any kind of funding for doing some kind of site activities?
Yes, there is. There are websites. There is Humanitarian Activities Committee website, IEEE Hack and IEEE Site.
Mm-hmm.
And in fact, the fund there's a funding for COVID response, which will stop on July 15th is the last date. So they have every quarter they have an application for funding opportunity, which can be explored by student chapters.
Okay, wonderful. Any questions or anything from any one of you?
Sir, one small question, sir.
Right.
Regarding technology in the healthcare, even though many things have come, especially in India, the doctors are hesitant to accept the technology. They want to go only conventionally. Any comment from you?
Yes, we were talking to the World Heart Federation, which is a part of World Health Organization, and they were too skeptical about taking adaptive technology. So there was a mental block. There was some form of resistance where the doctor has to physically check the patient before they can diagnose. But I think things have changed after post-COVID region. Post-COVID period, things have changed, and things may move faster with this remote diagnosis and monitoring schemes and things.
Thank you, sir. Thank you.
Welcome.
Any other question? Maybe we can take one or two quick questions or comments from others.
Yes, sir. Am I audible?
Yeah, Paulo. Yes.
Yes, sir. So I have a small question. So regarding a village, how you are getting this connectivity? Like how the data is being sent? Is it directly?
Well, I use a mobile. I use my laptop, and I connected the laptop to the net through my mobile phone, through the BSNL service. That was done in 2015. But right now things have changed. With Tesla launching the LEO satellites and for the worldwide internet coverage, and this PM-WAN network in India launched by CDOT, I think things have changed. It can be more useful, more effectively used.
So actually, I belong to some remote place in Assam, so where I did my undergrad. So there I was working with one of the villages. So in the village, the condition is really bad. So similar kind of condition is there. Even with internet connectivity, we tried using some SIMs to get connectivity, but we were still facing issues. So what are the alternates? Say if we don't have any mobile towers we connect through, are there any other alternates to get some kind of internet connectivity?
Internet connectivity, they used to use VSAT and those technology, but you can explore PM-WAN. Have you seen the PM-WAN? If you go to the CDOT website, you can check PM-WAN.
Sir, can you say the name again so that I could note it down?
PM-WAN.
Okay, thank you very much.
PM-WAN. Okay. That's Prime Minister WAN, Wireless Area Network, Access Network, like that,
Thank you, sir. Thank you.
Yeah. Maybe another quick question. Professor Anandan, if you want to ask or say something, please.
No specific question, but I congratulate the speaker for his great work.
Thank you, sir.
The research as well as applying this to the humanitarian
Thank you, sir.
problems.
Thank you so much.
That's all.
Thank you so much.
So, sir, if there is no more question, I believe that we can stop it over here. Yeah. We again thank the speaker once again on the behalf of IEEE MTT Student Branch Chapter IITBHU Varanasi, and we could be very happy to host you once this situation will improve and to have you over here. Okay, so and we also thank all the audience who have devoted their time to listen to the speaker, and I believe that every one of you have appreciated the talk, which has been both the technical as well as non-technical ones. So both of them have been equally appreciated. So thank you, sir. Thank you very much for the wonderful talks.
Thank you so much. Thank you to the organizer. Thank you, Shomak, for inviting me. Thank you to the stalwarts, Professor Raghavan, Dr. DC Pandey, Professor Anandan, for being there in my talk. It's really a privilege and a pleasure to see you all here. And thank you to all the students and the research scholars who spent their time to listen to this talk. So I really appreciate your presence. Thank you so much. And I look forward to meeting you all sometime in person.
Yeah, sure. We'll be very happy to do so.
And please feel free to write me emails and, if you have any queries and if I can be of any help regarding site or otherwise. Thank you so much. Okay, thank you.
And before we leave, let me tell all of you one thing, that Professor Siddiqui is now the ex officio member in the IEEE AP AdCom. So, am I correct, sir? So
yes, I'm as a member of the chair of the site committee. I'm a part of that.
So whomsoever is having any kind of problem or any kind of suggestion or any kind of comments or any kind of grievance, so please feel free to write to him. And let me, in fact, I don't know how many of you have interacted with him personally. Who didn't interact with him personally till date? Let me tell you that he is a person whom you can really approach and who is present everywhere to solve your problem. So let me just tell you that if you have any kind of questions in your mind, any kind of confusion, any kind of suggestion or whatever it is, please write to him regarding these IEEE AP issues. So I think he's the best person from India at the current basis to give you some kind of nice suggestions. So, and let me tell you again, as I have started the presentation, this particular session, that I consider myself very much fortunate that I have been taught by Professor Siddiqui from my very first year in my BTech course, and we are the first batch to be taught in all the years that throughout the BTech as well as master's course by Professor Siddiqui. So it is my real pleasure. Yeah.
Thank you so much. Thank you so much. Thank you. Thank you so much.
Yeah.
Thank you. Well.
So and let me tell you to all of you that yes, so the recorded meeting, it will be uploaded to the YouTube channel of the society. I have already shared to all of you by email the link of this particular YouTube channel. Maybe you can check a day or 2 days later from now onwards. Okay. Thank you, sir.
Thank you, Shoma. Thank you.
Yeah.
Goodbye.
Bye.
And good night, everyone.
Bye.
Bye. Bye. Bye. Bye.